So let's take a look at C403, which gave me trouble last time, but I've got it fixed. So I want to use Google Colab. You can use a local installation of Linux too, or of Python on Windows possibly, but I'd recommend using Colab to get a nice consistent environment. And the thing I learned is OpenSSL, modern versions, this feature doesn't seem to work correctly anymore. I couldn't find any explanation of how to do it, so I had to learn how to downgrade OpenSSL, something I'm reluctant to do, but this is what we do. We download, the Colab is an Ubuntu environment, so you can get these Ubuntu deb files and install them. So this here, if I run OpenSSL version here, you'll see that the OpenSSL version you have in Colab is 3 point something. And the version that does what we want is 1 point something. So we're going to make a local, we're going to downgrade it all the way down to 1.11f with these commands. These will just download precompiled. Let's see, I want to paste. Paste doesn't seem to be an option. How about Control V? All right, there we go. So this is going to print out the version, then it's going to download libraries and OpenSSL and 2 libraries it depends on, and then install them all. So you see it goes. So the original version was OpenSSL 3. And after it does all that stuff, it's now OpenSSL 1. And now the project will work. I don't know why they broke this feature in later versions of OpenSSL, but they did. So here's key generation. You choose 2 large primes, P and Q, then you multiply them together to make N, then you calculate Euler's tangent phi, which is P minus 1 times Q minus 1. You pick a public exponent that can be almost anything, and then you get the private key so that D times E is 1 mod phi. And when you're done, you have a private key which is going to have all these. This is the syntax from the official RFCs. You've got to have N and E and D and P and Q and a few other numbers here, as you'd imagine. All right, so we can generate one with OpenSSL. This will generate a private key. If I'm going to run it in Google Colab, I have to put an exclamation point before it because it's not a Python command, it's a shell command. But that's fine, and there you go. Generates a private key. So there it is. It's this blob of base 64 stuff, which includes all those numbers. And I'd like to show you how to take them apart, and you can take them apart with OpenSSL Gen RSA. So this is going with ASN1 parsing. So here we're going to generate another one, but we're going to put it in a file called key.pem. Then we're going to print out that private key, and then we're going to do the ASN1 parse, which will show us what's inside there. This is what failed last week. The ASN1 parse command doesn't seem to work correctly in modern versions of OpenSSL, as far as I can tell. Or else they've changed how it works, and I can't figure out how to make it work anymore. But this is using the old version. It should work. So it's going to generate a new key and show it, and then parse it. And, oops, you have to put an exclamation point before each of these things because they're not Python. There we go. If you're going to do it in this Colab environment. There we are. So there it's generated it. There it is. And here's what's in there. It's showing you the factors. This is E. You can spot it because it is 65,537 in hexadecimal. One looks like 10,001, which is in hexadecimal. That's what it is. This is N, the biggest one, the long number. And so I've got a printout here showing you how to interpret these. Yeah, the first big number is N, then this is E, 10,001, then comes D, P, and Q. And the other ones aren't that interesting. So this is N, E, D, P, and Q. And you notice P and Q are pretty small, 33 digits, and N is long, 64 digits, which is what you'd expect. All right. And I think this is the number of characters in hexadecimal. So anyway, so that's how you take that apart and see what's all in there. That's what this PEM format is just a base 64 encoded series of numbers with, I think, delimiters. I think the colons are in there to specify all these things. So now you can show the public key. Now the public key is calculated from the private key, and by the way, you can see it right here. The public key is just N and E, so it's just these two numbers, N and E. But when you want to distribute the public key to other people, you want to distribute just those numbers and not all this extra stuff which would break your security. So you generate a separate file, and this is how you do it with OpenSSL. So put an exclamation point in front of it and run that. And now you'll get the public key. And as you can see, here's the private key that includes all those values. The public key is much shorter because it includes only the first two values. And I could save it in a file and display it with ASN1 parse also. And that's what this will do. And again, I need an exclamation point in front of each line. All right. And so now, here it prints it out. There's the modulus and there's the exponent. For some reason, the printing out the public key is in a much friendlier format than this ASN1 parse thing. But anyway, there it is. I guess because this is the one you distribute to everybody, this is one you probably only have for internal use. All right. And of course, 512-bit keys were recommended, I think, back in the 70s and 80s. They're not considered safe anymore. These days, 2048 or indeed 4096 are recommended. So to make a longer one, you just tell it to make it longer. And you'll notice this will take longer to calculate. The time it takes may be noticeable now. 2048, it might still be less than a second. Got to put exclamation points in front of each command. All right. Nope, came out right away. All right. Anyway, there's the key. All right. Much longer, of course. And you can get the public key that goes with it. With the exclamation points. All right, and there you see, much longer modulus, but the same exponent, E, that we almost always use, 65537. All right. Now, if your private key is sitting in a file and you need it to decrypt traffic, but typically if somebody was to steal that file from your machine, you wouldn't want them to get in, so you can encrypt that key. This is called key wrapping, and you do it with, here you can do it. You can, this will encrypt it with AES 256 with this command here, and it's going to request a password from us to do that. So let's see if that works here. I think it should work fine as long as you put an exclamation point in front of it. Okay, that's going to run. It's now going to ask for a passphrase, so I can put in a passphrase like SSW0ID, right, then enter, and it got to put it in twice. All right, and now it's done. And if I want to see the key file, I have to do cat with a bang in front of it. And there it is. There's the private key, but it's encrypted using AES 256 CBC. And this, I suppose, is the IV, and there's the encrypted blob of stuff. So you need to know the password, which will be converted into a key by PBKDF2, I imagine, to get there. All right. If you want to display the public key, you're going to have to enter your password. So this is the way it will detect that it is encrypted and request the key from you. Put a bang in front of that. All right. It asks for the passphrase. If I put it in, then I get the public key. All right. All right. So there are some challenges here where you get to find things. The first few are just straightforward, where you have a private key and you can find things from it. You have a private key, you find P from it, you find a public key from it. Then here you have to start filling in things where parts of it have been corrupted. You see I've replaced part of it with X's, and you have to figure out information based on just what you can find here. And this one's easier, this one's harder, but those are where you get to fill in find the numbers you know and use them to deduce the numbers you don't know. And down here you will have to do a brute force search for some of it, because some of the numbers you need have been partly corrupted. So There's huge challenges to solve, and that's what I wanted to show you. And as you can see, you can do it even on modern systems like Colab by downgrading your OpenSSH back to a version that works. I hunted and I could not find any article explaining why they broke this feature in OpenSSL 2 and 3. There may be a blog or something somewhere explaining it, but I couldn't find it. So I took the unhappy result of actually downgrading to an earlier version. That's it.